Let us look at what happens next. We'll look at one more sequence. So currently both of them are in the shared state with the updated value. The memory is also updated with the latest value. Now let us say we have a processor write request for that uh, location from P2. Now what should happen here ideally is if I write to this data, then this data will become inconsistent with the memory and inconsistent with P1. So if it's in the shared state and I have a processor write request, I need to change it to modified state. That's because it's going to be inconsistent with memory. So that's the first thing. So I'm going to change the state from shared to modified. So modified always comes in when you do a write. So you should remember that I can get to the modified state from either I or S, and that is going to come only when I do a processor write. So exclusively, this is exclusively for writes. So when I do writes, I'm going to change it to modified state. So if I do reads, I'm going to be in the shared state. Okay, or if I am currently in the modified state and I do a read, I'm going to keep continuing in that state. So basically, if I'm going to change to modified state, if the cache block is going to change to modified state, it's always when you do a write to that cache line. So looking at this diagram, we're going to change this state from shared to modified, and we're going to write this value. Now what happens to this other block in this P1? So ideally, because we are doing an invalidation based protocol, I need to send some signal onto this bus to invalidate this value. So I'm going to invalidate it and change the state to I. You can also see that in this diagram. Currently, this other core, I said that this diagram is for the other core, which is seeing the bus request. Now the bus request that is coming in here is called a bus upgrade. Now this bus upgrade signal means that this processor needs exclusive access to this cache block. So if we go back to our set of definitions here, bus upgrade is sent when there is a write hit in a processor's cache and it sends a bus upgrade request. And this means that we want to invalidate the block in the other processors. So this is the meaning of bus upgrade. So let us go back to this bus upgrade. So we send a bus upgrade on the bus. Now this bus upgrade is seen by the other processor P1. P1 is in the shared state. So I come to this diagram here. In the shared state, it sees a bus upgrade and it's going to move to invalid state. So you could just use this diagram blindly, or you could just use your own logic to come up with this change in the states. Now let us go through one more iteration. So currently this is in the invalid state and this is in the M state. So I start with that state, I and M. Let us say that processor 1 tries to read from that block. So again, if it's in the invalid state, it's going to send a bus read on the bus. So there is a processor read from the processor and a bus read. So I'm going to change to shared state. Now what does this processor 2 do? Processor 2 has the latest copy. So it is in the M state. It sees a bus read and it sends the data to this cache. And the same steps follow as we described earlier. It's going to send a flush to uh, the bus. It's going to write the updated value and then change the status to shared state. So we are again back to the same place. All of them are in the shared state. So alternately, let's say instead of a read, let's say I go back to the same previous state, I and M, and the bus and the processor 1 wanted to write instead of read. So what would now happen? So like I said earlier, if it's in any state and you want to write to the data, you're going to change to the modified state. So I is going to change to M, and you're going to have the latest value here. And we're going to send a bus upgrade. This bus upgrade is going to invalidate the other data. So looking at this diagram, so what we should also observe is what is happening with P2. So P2 is in the M state, and it sees a bus upgrade. Okay, sorry, this should ideally have been a bus read X signal, not a bus upgrade signal. So this should have been a bus read X. So what does bus read X mean is that processor is trying to write to that cache, but that is a cache miss. So it's trying to write to the cache, but this cache block is a cache miss. So if we go back to our previous definitions here, so bus read X is when a write miss occurs in a processor's cache, it sends a bus read X request on the bus. And this is going to return, this will return the cache block from the either the memory or from the other cache. And it gives, so this is going to return the, sorry, this is going to return the cache block, and it is going to give exclusive write access to this particular processor. And if the data is present in other caches, it has to invalidate. So what this means is, let us go back to this. So this is a cache miss, and therefore it sends a bus read X signal, not a bus upgrade. So bus upgrade would be sent if it's a cache hit. So if you look at this diagram here, this was a cache hit and it was trying to write to it, and therefore it's a bus upgrade signal. Whereas here it's a cache miss because this is invalid, and therefore you send a bus read X. Now what is happening with P2 is that it is in the modified state. So it's in the M state here, and it sees a bus read X. So remember that P2 has this block in modified state, which means this was the latest value of the memory. And that needs to be written back to this memory to allow precise exceptions. So at this point, if there's an exception, the memory should have the up-to-date value. Therefore, this core, before changing to invalid state, has to write that value back, and that is happening through this flush signal being issued on the bus. It is going to write back the value before it's going to change the invalid state. Okay, so we have now described bus read, bus upgrade, and bus read X, and also the flush signals on the bus. So let us alternately see the same I and M state, but let's say P3 wanted to write. Now P3 wanted to write. So if P3 wants to write, again, it is in the invalid state, which means it is going to be a cache miss, and therefore it's going to issue a bus read X signal. Now the I state is going to change to M state, because whenever we want to write, we're going to change to M state and write the new value. Similarly, what do the other processors see? Let us do it step by step. Let us see what happens with P1. P1 is in the invalid state and it sees a bus read X. So let us look at this diagram. P1 is in invalid state and sees a bus read X. So no change, it continues in the same state. It continues in the I state. P2 is in the M state and it sees a bus read X. So P2 is in the M state and sees a bus read X. So it's going to send a flush signal on the bus and move to M state. So it's going to send a flush signal on this bus, and it is going to write the value back to the memory to maintain consistency, and it's going to change its state to invalid. While what is processor 3 doing? It is changed from I to M state, writing the latest value. So this is how this works, and this is how the MSI protocol works. It's not too complex. You just need to know, just have a logical way of how thinking how which processor needs to access the data and which cache should have the latest copy and so on. And similarly, you could also very conveniently use these two FSMs. And the only thing is you need to understand which FSM to look for. So whenever the processor is writing or reading to a particular cache, you look at the first FSM. And what does the other processors see when they look at the bus signal? So you should use the second FSM to change the states of the other processors. So you could now try out an example on your own. So this is the sequence I've given. First is you assume all of them are in the invalid state. You issue a read for the from processor 1, that is R1. Then you issue a read from processor 2. Then write from processor 3, read from 2, and so on. So do work out this sequence for this MSI protocol. So to summarize the invalidation based protocols, firstly, it is ensuring that a processor has exclusive access to the data before it writes to it. That is why we are changing the status to M state. So M state actually is giving exclusive write access to the processor before it writes to it, and therefore we are invalidating all the other copies. So that is why it invalidates all the other copies when a certain processor writes to it. Then exclusive access ensures that no other readable or writable copies exist in other cores, and therefore you invalidate all of them. And to perform an invalidate, how does it happen? The processor which is trying to write is acquiring bus access, and it broadcasts the address to be invalidated, and each controller is going to invalidate its own copy. So how that happens is all the processors are continuously monitoring the bus and watching for the addresses. So if the processor finds that there is a certain address in this local cache, it's going to invalidate its local copy. And let's say what happens if two processors are trying to gain access to the bus. Two processors are parallelly trying to access the bus. So what happens is the first one is going to gain priority. So what are the challenges with this invalidation based protocol is if you have more than 8 cores, then uh, the bandwidth at the caches and the bus is going to be a bottleneck. So that's a tough problem to solve. Then the other problem is every cache must try to examine every miss and the request placed on the bus. So if there are more than 8 cores, it's going to be difficult. So solution is, like I said, you have what is called a directory-based protocol. So Intel i7 in Xeon series has this directory-based protocol. It maintains a directory with the cache status at the last level cache, and all the caches, all the processors will look at this directory. AMD Optron uses a mix of the Snoop and the directory based mechanism. So it basically tries to use the broadcast mechanism to find if there are any shared copies in other cores. But it also uses this acknowledgement based mechanism to figure out what is the ordering of the writes or ordering of the reads. So that is a mechanism in the directory based protocol. So it uses a mix of both of them. And to increase the communication bandwidth between the processors and the memory, you could have multiple buses or multiple types of interconnects, crossbars, and different types of networks to increase this communication bandwidth.